In this session, we are going to introduce spectral clustering method. Why do we want to do spectral clustering? Because spectral clustering have some unique advantages. So first, spectral clustering makes no assumption on the shapes of clusters. So you can cluster like any kind of a shape, even intertwined spirals. You will be able to find nice and neat clusters, not to say other shapes. However, many other clustering algorithms like k-means or EM tend to find non-convex shaped clusters. Then another advantage is usually EM or like k-means, those algorithms require an iterative process to find local minimum. And they are very sensitive to initialization, so you usually need multiple restarts to get high quality clusters. However, spectral clustering where you have no such burden, the general process of spectral clustering is partitioned into these three steps. The first step is construct a similarity graph. For example, we can use k-nearest neighbor based on their neighborhood using like a Euclidean distance or other distances you like to do your clustering. Okay. Then for all the points, you can construct such similarity graph. For example, if you look at this illustrative example, you can see the original data points. If you do symmetric k-nearest neighbor, you will find this k-nearest neighbor graph like the following. Then we can embed the data points in a low-dimensional space using spectral cluster embedding. What is this? This essentially is we can do graph Laplacian, compute the eigenvectors of such graph Laplacian. After this embedding, the cluster structures become more obvious. Then we will be able to apply classical clustering algorithm like a k-means on these embedding. That means we will be able to partition the embedding graph into nice clusters. So this is the general idea. Now we look at how we do it step by step. First, suppose we have a graph. This usually is obtained by the k-nearest neighbor. Then we get the weights. Suppose the weight W sub 1, 2 is the weight connecting the vertices 1 and 2. Okay. Then the adjacency matrix is an m by n symmetric matrix like this one. Okay. Then for each element, what you got, the assignment is if there's an edge between like a 1 and 2, then you can, based on the edge weight, W sub 1, 2, you can get that weight. W sub ij is the weight of this cell. Okay. If there's no connected edge, like 1 and 4 is not connected, then 1 and 4, this cell will be assigned as 0. Okay. Then we can perform Laplacian on this matrix. Essentially is we use a diagonal matrix of degrees minus this adjacency matrix, we'll get a Laplacian. Okay. What is diagonal matrix of the degrees? Simply says the degree is defined by, for each row, you just sum up all the degree, all the weights, or you say all the cell values in this row. For example, for row 1, what you get is W sub 1, 2 plus W sub 1, 3. You get the weights, that's the degree you will get. Okay, that's D1. Similarly, for other degrees, you just calculate it in the same way. Laplacian, this matrix value is, if this one is diagonal matrix I equals J, then you get the D sub I. Okay, that's the row value of this degree. If it's other cells, like ij has an edge, then because 0 minus this W sub ij, you get minus W sub ij. That's what you get. If originally was 0, you will still get 0. Okay. So that's the value you got from calculate this Laplacian matrix. Then we can see how we can calculate the graphs for eigenvalue and eigenvector. Okay. So we can see the eigenvalue computation is based on this formula, which has been used very popularly in linear algebra in matrix computation. Okay. We're not getting into very detail, but the general philosophy is you get a matrix A. Lambda is the eigenvalue of A. And for some vector v, you will follow this equation. And v is eigenvector, and lambda is the eigenvalue of A. Okay. So then for a graph G, if we have n nodes, then its adjacency, you will have n eigenvalues, and this n eigenvalue, you can sort them according to the descending order. You get lambda 1, lambda 2 to lambda sub n. Of these n corresponding eigenvectors will be x sub 1 to x sub n. You look at this figure 1, you can see this is the original graph. We have 6 vertices and their connections. Weighted connection is marked using those values. Okay. Then obviously the original matrix, adjacency matrix, is marked here, you can see, and that's the original adjacency matrix. Then we can calculate this originally this matrix eigenvalue, and you can see this is their eigenvector, and this is their eigenvalue. And you probably see this is mu 1 to mu 6. Okay, so that's the spectrum of the graph. Okay. Then the eigenvalue and eigenvector of the graph Laplacian of G is calculated for this graph. Essentially is you get a lambda 1, lambda 2 to lambda n, and we know the value lambda 1, lambda 2, lambda n. We can sort them in this order. Okay, so if this is 0, you get a spectrum is you get this lambda value, that's eigenvalue and eigenvector. Then eigenvalue reveals a global graph property which is not apparent from the edge structure itself. Essentially, if you get a 0, it's the eigenvalue with k different eigenvectors, you probably will see these essentially is the k connected components. That means if lambda 1 is 0, that represents one connected component. Okay. Then if a graph is connected, then lambda 2 will be greater than 0. Lambda 2 is algebraic connectivity of G. Here you can see L sub G has lambda 1, lambda 2, lambda 3 as 0. You get 3 connected components. And if you have this G1 and G2, you probably can see G1 has only one connected component, and G2 also has one connected component. That's why lambda 2 is greater than 0. However, you also can see G2 is much denser, much more connected than G1. That's why G2's lambda 2 value will be greater than G1's lambda 2 value. Okay. Then we can work out the partitioning via spectral methods. The general philosophy is if we get this original graph, we map them into Laplacian of this original graph is this value. Okay. Then we actually also know we can calculate the second eigenvector, and the second eigenvector v sub 2 corresponding to lambda sub 2. And for lambda sub 2, the smaller, the better quality of the partitioning, because if lambda is 0, means it's not connected. And if lambda 2 actually is greater, means they are more tightly connected. If you want to get nice partitioning, you want to find a smaller lambda 2. Then if we calculate this for each node I in G, we can assign it the value V2. Then V2 sub I. So for example, this node 1's V2 is 0.1, 0.41. Then if we want to find, these are the 6 nodes, their corresponding V2 value, then if we get this V2's value, we can get it greater than 0, then we can assign to C1, and these V2's value is less than 0, it could be another cluster, then we actually will get a nice partitioning. C1, C2, this 1, 2, 3 will become one cluster, 4, 5, 6 will become another cluster. So we can extend this algorithm to K partitions. The Yang, Jordan, and Weiss algorithm, worked out by Andrew Ng, Michael Jordan, and this published in 2002 was a normalized Laplacian. Essentially, the original Laplacian you is not a normalized, but once you use this formula, you can normalize the graph so the degree that part is all 1, and all the other rows you add up, actually it's -1, so you finally get a normalized graph. So we can compute the first K eigenvectors, V1 to Vk, then we can calculate the matrix. In a similar way, we can do the partition into, because we take the ith row of U as its feature factor after normalizing to norm 1. Then we can cluster the points with k-means into k clusters. And this method is commonly used as a dimensionality reduction methods for clustering.